Exercise 1028 is trying to get you to think about a really special reaction called alkylation. This is the only reaction that we'll learn this semester that you can use to create a new carbon-to-carbon bond. Alkylation, you would see from the recipe sheet that we have, uses a terminal alkyne. Now, there's a hydrogen on a terminal alkyne. Let me actually draw that in below this, and I'll draw that in a separate color. So that carbon there has a hydrogen attached to it, and if you treat it with a strong base, so something like sodium amide that we have here, then that amide, the NH2, with its full negative charge, can act as a base and steal that hydrogen. The electrons in that bond snap back onto the carbon in the triple bond. Now, the reason why this can happen, because carbon is not the best, is not able to handle a negative charge, so usually it's not thought of as very acidic. It won't give up hydrogen most of the time because it's hard for it usually to handle this negative charge. The reason why this can happen here is because this carbon is sp hybridized. And if you remember, sp orbitals are really stubby. They're 50% s. And so they hold that lone pair really close to the nucleus. The nucleus is where the node is. So the nucleus is there. And the nucleus has all the protons, all the positive charge. So that sp orbital is really stubby. It pulls the electrons close to the positive charge in the nucleus and stabilizes them. So because that carbon is sp hybridized, it ends up being slightly acidic. Now, what's really special here about that is that you now have a carbon that can act as a nucleophile, and so it can undergo any substitution reaction. You could take any carbon chain, and remember the symbol for that is an R, and all you need is a halogen. Remember, the symbol for any halogen is capital X. So that could be, just to be more concrete, let's use bromine. So any carbon chain, and this nucleophile can come in, nucleophilic attack, and kick the leaving group off, loss of a leaving group, at the same time, and do an SN2 reaction. And what you do is you create a new carbon-to-carbon bond. And that is profoundly special, because organic chemistry is the chemistry of carbon. The shapes of these different carbon compounds determine what pockets they can fit into, what receptor sites they can fit into, and therefore what they can react with. So when you can create new carbon-to-carbon bonds, you can change the shapes of molecules, and you can determine what types of receptor sites the molecule will fit into. So it's a really special reaction, this one here. Now, I did say that this could be any carbon chain, but watch out, this is an SN2 reaction, which means that this will work best if that's primary, and it'll still work if it's secondary, but it won't work if it's tertiary. So just make a note of that. Okay, so we're going to be using this reaction. We walked through the mechanism here. We're going to be using this reaction over and over and over again in these next exercises in 1028. What they say is starting with acetylene, and that's a common name for really, if the IUPAC name would be ethyne. It's very common, though, acetylene, just two carbons with a triple bond between them. And what you'll notice is that in the case of acetylene, there's a hydrogen on each side. So technically, you can create two new carbon-to-carbon bonds here by using that sort of recipe that we talked about below, that alkylation. Acetylene, interestingly, is the molecule that they use in welding torches when they burn them. When the flame in welding torches is created by burning acetylene molecules. It's a good name to know. Sometimes tests like the MCAT or PCAT or DAT will expect you to know that acetylene is really ethyne. Okay, so what we want to do is to use this molecule, and we want to turn it into different things, depending on which part of this exercise we're doing. In part A, we want to turn it into 1-butyne. Now, when you're drawing triple bonds, when you're drawing alkynes from the name, I kind of encourage you to draw the triple bond first, because you know it has to be linear. Now, And so it can be tricky if you don't draw it first. So if we have the triple bond, we know we have it. Where does it start? Right in front you have that 1 there, so that means it starts on carbon number 1 and goes to carbon number 2. Okay, how many carbons do we have total? The prefix is bute, and so we have 4. So that's 3 and then 4. 3 and 4. So we want to turn acetylene into this 1-butyne. And if you compare them, you'll see that the only difference, well, first you have a couple things that are the same. You have these 2 carbons that are the same, and this hydrogen, so those are all there. But you've changed one thing. You've changed this hydrogen, and you've replaced it with 2 carbons. So how can you do that? Well, the first thing is, you can do that through alkylation. And the first step is to turn this carbon into a nucleophile by treating this with a strong base, like sodium amide. Once you do that, this turns into a nucleophile, carbon nucleophile. And then think about how many carbons you want to add. Here I want to add 2, right? 1, 2. So I draw 2 carbons, 1, 2, and then I just put a leaving group on one of them. And so when this reacts, this will attack that carbon with the leaving group, kick the leaving group off. So standard SN2 reaction, and what we're left with is our product. So if you sort of number this, you could see this would be 1, 2, 3, and 4. 1, 2, 3, and 4. So overall, the recipe to make this transformation happen is to take the acetylene, treat it first with sodium amide to turn it into a carbon nucleophile, and then treat it with whatever carbon chain you specifically want to add. And here that was an ethyl group with a leaving group on it. And it could be bromine, it could be chlorine, it could be iodine, just a good leaving group. And that's your answer. That's your recipe. Okay, so we're going to take this acetylene again, and we're going to do more reactions with it. We just saw how to turn it into 1-butyne. How could we turn that into 2-butyne? So 2-butyne, draw the triple bond first. Because it's starting on carbon number 2, this will be 2 and it'll go to 3. Now because the prefix is bute, we know that we need 4 carbons total, so 1 to the left, 1 to the right, that gives me 4. Notice it has to be linear. Okay, well what we see here are 2 new carbon-to-carbon bonds. Sure, the carbons, these 2 carbons stay there, but both of the hydrogens are replaced by methyl groups. So we go through the same process we've been through before. First, take one of the hydrogens off by treating the molecule with sodium amide. So now, we still have one hydrogen, but the other one got ripped off and has a full negative charge. Then, treat that with whatever carbon you want to add, here it's just 1, attached to a leaving group. So here I'm going to use bromine. So this can attack the carbon, kick the leaving group off, and what we have at that point is a new carbon-to-carbon bond on one side. We still have the hydrogen on the other. Now we want to replace that hydrogen with another methyl group, so we go through this process again. First, we rip that hydrogen off using sodium amide. And that turns our molecule into a carbon nucleophile. Then we just have to take the group that we want, a methyl group, and have a leaving group on it and mix it with the molecule we have. The nucleophile will attack the carbon, kick the leaving group off, and there it is. We have our product with a new carbon-to-carbon bond. So overall, you would want to separate this into steps. First, you would treat the original molecule with sodium amide. Second, you would add however many carbons you want to add with a leaving group on it. So we just wanted to add 1. That gave us this molecule down here. We wanted to replace the other hydrogen with another methyl group. So first we rip the hydrogen off with sodium amide. Again, notice this is a separate step though. And finally, you treat the molecule, this carbon nucleophile that you made, yet again with a methyl iodide or methyl bromide, because we want to replace the hydrogen with a methyl group. So we want just 1 carbon there with a leaving group on it. And this would be the full recipe for turning acetylene into 2-butyne. Okay, so let's take this acetylene again, see what else we can do with it. What if we wanted to make 3-hexyne? Okay, so acetylene is really ethyne. It has the 2 carbons with a triple bond between them. What if we wanted to turn that into 3-hexyne? Well, because of the infix, you know you have a triple bond. And because of the 3, you know that this starts on carbon number 3, then goes to carbon number 4. The prefix is hex. That means we have 6 carbons total. Well, we know we have to go back to 1. So there's 2 and 1. And then we have to go to 5 and 6. 5 and 6. Now notice that the bonds coming off of the triple bond are linear. It's really important. Okay, so if you compare these 2 molecules, if you compare acetylene with 3-hexyne, you'll see that there are some similarities. You have the 2 carbons in a triple bond in the middle. But that's where the similarities end. You replace one of the hydrogens with an ethyl group, you replace the other hydrogen with another ethyl group. In other words, you form 2 new carbon-to-carbon bonds. And you form each of those through alkylation. So you can take this, rip one of those hydrogens off. We want to replace it after all. We rip it off with a strong base like sodium amide. Then we have acetylene, but a nucleophile. We have a carbon nucleophile. So we can take whatever group we want to replace the hydrogen with, and here it's a 2-carbon group. So 2 carbons, and put a leaving group on it. Just to prove the point, I'm going to put a different leaving group than before. Here I'll put iodine. So when you have that, this carbon nucleophile could attack that carbon, kick the iodine off in a standard SN2 reaction, and what we have here is 2 carbons added on the right side. The hydrogen is still there on the left. Okay, well, and actually let me make this look a little bit more like what we have in the product. So 2 carbons there. So we have this product on the right side already. Now we just have to replace the hydrogen on the left. First, let's rip it off. We rip off a hydrogen by adding a strong base like sodium amide. And that turns that terminal carbon, the end carbon on the terminal alkyne, into a nucleophile. Then all we have to do is take the carbon chain that we want to add, has 2 carbons on it, and use a leaving group. Here I'll use iodine again. Attach a leaving group on it. Then this carbon nucleophile will swoop in, attack the carbon there, kick the leaving group off in an SN2 reaction, and you end up with your product. You've done alkylation twice. You've formed 2 new carbon-to-carbon bonds. So overall, you want to separate each of these recipes into each of these steps into separate numbered steps in a complete recipe. So to make the whole transformation happen, you'd first want to add sodium amide. Then, so that'll give you your carbon nucleophile, then give it something to attack. The carbon chain you want to add with a leaving group on it. That takes care of 1 carbon chain. Now we have to do the other one. So first we rip that other hydrogen off with sodium amide. And we follow that up once we have our carbon nucleophile with whatever carbon chain we want to add. Here an ethyl group, so I'll just add a leaving group on it. And this recipe here would allow you to turn acetylene into 3-hexyne. Okay, let's take that molecule. Let's use it to try to make 2-hexyne. So if we have acetylene, how can I use acetylene to make 2-hexyne? Well, first let's draw 2-hexyne. Because of the infix, we know that we have a triple bond. Because of the 2 in front, we know that this is going to start on carbon 2 and go to the next carbon, carbon 3. Now, we know that there has to be a carbon number 1, so we put that on the left. And because of the prefix, hex, we know that there are going to be 6 carbons. So here's 4, 5, 6. And I can number it just to check. So there we have 2-hexyne on the left. Okay. So what can we do? Well, when you look at the different, when you look at these 2 molecules, you'll see some things are similar. You have those 2 carbons and the triple bond in both of them, but other things are different. You replace the hydrogen with a carbon chain on one side, and you replace the hydrogen with another carbon chain on the other. And so you've formed 2 new carbon-to-carbon bonds, and so you have to do alkylation twice. The first thing you do to replace this hydrogen with a carbon chain is to rip it off using a strong base like sodium amide. So that will give you, if you just use just one equivalent of that, you'll only take one hydrogen off and you'll have this carbon nucleophile. Then you need to react that with whatever carbon chain you want to add. So here we have 3 carbons, and we want it to add on the end. So I'm going to add 3 carbons, 1, 2, 3, and on the end I'm going to add a leaving group. And here, just to emphasize the point, it could be any leaving group, I'm going to use chlorine. So this nucleophile swoops in, attacks the carbon, kicks the leaving group off in a standard SN2 reaction. And so what we'll have is this molecule here. We've replaced the hydrogen that was here with 3 carbons, a propyl group. Now we're halfway there. We've added one of the carbon chains, we just have to add the other. To do that, we have to rip the hydrogen off first. We do that by adding sodium amide. That strong base steals the hydrogen, and now we have this carbon nucleophile. All we have to do to get our final product is to take the carbon chain that we want, and here it's a methyl group, and just add it to some sort of a leaving group. Then the nucleophile swoops in, attacks the carbon, and kicks the chlorine off, leaving you with your final product. So we did 2 alkylations. First, we treated acetylene with strong base sodium amide in order to turn one of the carbons into a strong nucleophile. Then we reacted it with the carbon chain we wanted to add, just with a leaving group on it. That took care of one half of the molecule. Then we had to make the other half react. So we treated it with sodium amide again, NaNH2. That turned that carbon into a nucleophile. We reacted that with methyl chloride. So we took the carbon chain that we wanted to add and just put a leaving group on it, and that whole recipe allowed us to turn acetylene into 2-hexyne. Okay, let's see another one. Let's see if we can turn it into 1-hexyne. So first let's draw that. How do we turn this into 1-hexyne? Well, we know that we have a triple bond because of the YN. Because the number 1 is in front of the backbone name, that means it starts on carbon 1, it goes to the next one, carbon 2. Well, we have 6 carbons because the prefix is hex. So 3, 4, 5, 6. That is 1-hexyne. 3, 4, 5, 6. Well, when you compare this 1-hexyne with the molecule that we have on the left, we see a little bit, quite a bit that's similar. We have the 2 carbons and one of the hydrogens in common. What's different is what's on the other side. This one hydrogen turns into a 4-carbon chain or a butyl group. Well, all we have to do to replace a hydrogen with a carbon there and form one new carbon-to-carbon bond is alkylation. So we rip the hydrogen off with sodium amide, a strong base. That gives us this nucleophile, carbon nucleophile, and then we just have that attack the same group we want to add, so that has 4 carbons in it, 1, 2, 3, 4, just put a leaving group on it. And here we'll use bromine. So the nucleophile attacks that carbon, swoops in, and kicks the bromine off. And we end up with our product. Triple bond with 1, 2, 3, 4 carbons on one end. So overall, we only had to do 1 alkylation here. We treated our molecule first with sodium amide to turn one of the carbons into a good nucleophile, and then followed it up with the carbon chain we wanted to add with a leaving group attached. And that recipe would allow us to turn acetylene into 1-hexyne. Okay, let's try turning acetylene into 2-heptyne here. So how would we do that? Well, we know we have a triple bond, so let's start by drawing that first. Because we have a 2 in front, that means the triple bond starts on carbon 2 and goes to carbon 3. We want to draw this linear, so carbon number 1 will be going straight out, and carbon number 4 will be going straight out. After that, we can zigzag. Because the prefix is hept, we have 7 carbons. So we already have 4 written. Here's 5, 6, 7. So you can number it just to make sure. there is 2-heptine. So when we compare 2-heptine with our original molecule, acetylene, we see some similarities and some differences. The 2 carbons in the triple bond are still there, but the hydrogens have changed. They've been turned into carbon chains, and 2 new carbon chains, 2 new carbon-to-carbon bonds have been formed. Well, to make new carbon-to-carbon bonds, you use alkylation. First, treat your terminal alkyne with a strong base like sodium amide that rips the hydrogen off and turns the carbon that it was on into a nucleophile. Very special thing, carbon nucleophile. Once you have the carbon nucleophile, look at the carbon chain you want to add. Here we have 1, 2, 3, 4 carbons. So we're going to take a 4-carbon chain, 1, 2, 3, 4 carbons, and we're going to add a leaving group on it. Let's use a chlorine. The carbon nucleophile will swoop in, attack the carbon, and kick the chlorine off. SN2 reaction. What we have at this point is a terminal alkyne with 1, 2, 3, 4 carbons on it. So we've accomplished one transformation. We have this group on the right. What we don't have is the methyl group on the left. So we take that terminal hydrogen there and we rip it off by using a strong base like sodium amide, NaNH2. And that creates this carbon nucleophile here. To get our final product, we just take the carbon chain that we want, there's just 1 carbon there, and put a leaving group on it. This carbon nucleophile attacks the carbon, kicks the chlorine off, and there it is, 2-heptine. So, all we needed to do to make this transformation happen was first turn the carbon into a nucleophile, the end carbon into a nucleophile by adding a strong base like sodium amide. Then we added the number of carbons we wanted, 4, 1, 2, 3, 4, with a leaving group. We did an SN2 reaction and replaced one of the hydrogens on acetylene with a carbon chain, and we just had to replace the other one. We ripped the hydrogen off again with sodium amide in a separate step, and finally, once we have that carbon nucleophile, we look at the carbon chain we want to add and just draw it with a leaving group on it, and that gives us a recipe that creates our transformation. That recipe will allow you to turn acetylene into 2-heptine. Okay, let's try this one, and I think, well, let's see, we've got a few more. So we'll do this quickly. Okay, so 3-heptine. You draw the triple bond. It starts on carbon 3, goes to 4, so you'd have 2, 1, 5, 6, 7, 8. Oops, 7. So 5, 6, 7. So that is 3-heptine there. Okay, now I'm going to start to do this in a more abbreviated way because we've already done so many examples. So let's try to do it more quickly. We can take this last hydrogen off by using sodium amide, NaNH2. That creates the carbon nucleophile. Then we just look at the carbon chain we want to add. Notice this has 3 carbons. So we're going to have 3 carbons, and then a leaving group. So those 2 steps will create this part of the molecule. To create the other end, we rip this other hydrogen off using sodium amide, and we follow it up with however many carbons we want, here 2, with a leaving group on it. And that recipe will allow you to create that transformation, really through 2 successive SN2 reactions. Okay, let's try to turn acetylene into 2-octine. Now, the YN means we have a triple bond. It starts at carbon 2 and goes to carbon 3. That's what that 2 in the front is telling us. So we have a carbon 1 on the end, carbon 4, 5, 6, 7, 8. So there is 2-octine. Now, if you want to turn acetylene into 2-octine, you just have to do 2 alkylations. First, rip 1 hydrogen off with sodium amide. Then, look at how many carbons you want to add. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. And then put a leaving group on it. And so that allows us to create the right side of this molecule. Next, we want to create the left side, so we rip the hydrogen off with sodium amide. And we look at how many carbons we want to add, just one. Put a leaving group on it, and that recipe will allow you to create 2-octine out of acetylene. All right, so then we have I. So we can take acetylene there. We want to turn it into 2-pentyne. Because of the YN, we know that we have a triple bond. Because of the 2, we know it's starting on carbon 2, going to carbon 3. So we have 1, 4, and then we have 5. So that's 2-pentyne. Okay, so what we can do, we see that we're making 2 new carbon-to-carbon bonds. So what you can do is take sodium amide, that will rip this hydrogen off, turn it into a carbon nucleophile. Then look at how many carbons you want to add, here that's 2, and just put a leaving group on them. That takes care of this right side of the molecule. Next, we want to replace that hydrogen with a methyl group. So we treat it with sodium amide, that strong base rips the hydrogen off. And next, we take the carbon chain we want to add, so just 1 carbon, and put a leaving group on it. It does an SN2 reaction, and you end up with your product. So that sequence of steps would let you turn acetylene into 2-pentyne. Okay, how about this? What if we wanted to create this from acetylene? Well, the process is really similar. It's almost the exact same. So first, what you'd want to do is treat the molecule with sodium amide. That will rip the hydrogen off. Then look at the carbon chain that you want to add. Here there's just 2 carbons. So we have the 2 carbons and put a leaving group on it. Those 2 steps will create the right side of this molecule. Then, to create the left side, we want to replace the hydrogen with all this stuff. So we rip the hydrogen off with a strong base like sodium amide. Then we have a carbon nucleophile. All we have to do is react it with this, just with a leaving group on it. It could be any leaving group. And if you do that, you will end up with your final product. So that this would be a recipe for making this molecule here out of acetylene. Okay, so again, what if we want acetylene? We have acetylene and we want to create this molecule out of it. Well, what we want to do is take this hydrogen and replace it with this weird group right there. So we have to rip the hydrogen off with a strong base like sodium amide. Then look at the carbon chain that you're adding. It's this 6-membered ring with alternating single and double bonds with a methyl group on it. And then just add a leaving group onto that. Those 2 steps will create the right side of this molecule. Then we want to replace this hydrogen with a different alkyl group, or with another alkyl group. So first we rip the hydrogen off with a strong base like sodium amide, and then we just redraw this same group, but we put a leaving group on it so that we can do an SN2 reaction. And this recipe here will allow you to create this interesting molecule from acetylene, the simplest of the alkynes. So hopefully this exercise has given you, has made you feel more comfortable with using this alkylation reaction to create new carbon-to-carbon bonds on terminal alkynes.